Okay. So Fubini theorem tells you that double integrals can be computed as iterated integrals actually. Okay.
So what do you mean by nice function?
By a nice function which satisfies the condition of, the Fubini theorem, continuity and defined in a, good region. By good region you mean a, Fubini region and must be rectifiable, so on and so forth.
अगर ये पॉइंट बीच में होगा कहीं
So it's really common sense. So think about it. So if this point is here, so I'm going to say, okay, stay away from this point and stay away from this point and compute integral here and add them. And bring them together. For that you don't need to be, you just have to think common sensically, okay? Common sensically. Now I'm going to write a miraculous theorem actually. You're going to say, it just makes your life easy. Absolutely easy. Okay? That if you want to, so the miraculous theorems can be interpreted in many different ways. But the key thing is, we are very happy with the line integrals. This miraculous theorem is going to tell us that if you want to compute a double integral, you can turn it into a line integral and compute it. And if you have a line integral, you can turn it into a double integral and compute it. So really it just connects these two different species actually, which apparently looks different. Okay, so you call it a Green theorem. Move to the Green theorem. So now we will transit from Fubini region to another kind of a region, it's called the Green's region. Okay, so then you're going to have a lot of regions. Okay? हमारे यहाँ कॉलोनियाँ होती है ना, गुलशने फलाना और गुलशने फलाना. So you have different regions. Anyway, so here's the thing. Imagine I have a type 1 Fubini region. Okay? I have a type 1 Fubini region. Okay? And I want to play with it. And I have the usual assumptions that okay, this is like your phi 1 and phi 2 and x equal to a and x equal to b, so everything is same as previous one. Okay, the notation is same. Now, I mean, if you look at the regions, the boundary of the region actually, how does the boundary of region look like? What are the boundaries in its fundamental nature? Kya hai? Boundaries. So they are curves actually. So I can see that I have a Fubini region with the 4 curves as a boundary. Okay. So if I want to parameterize this curve, question is what should be the parameterization of it? So let me give this a name, say C1. Okay. And so let's give this name as C2 curve. Let me give this a name C3. They have nice anti-clockwise orientation actually. Okay. Question: what should be the parameterization? The path that represents the curve. I'm sorry. You can keep it any direction. I mean, these are the curve, okay, but you can give them any direction, okay. But finally, so मैं इनको इस सब अलग-अलग क्यों रख रहा हूँ? So I'm not putting them, I'm not giving them, one particular orientation. So I want to show you that even if they doesn't have same orientation, I can turn them into the orientations. What I just need to do actually. So for example, revert it and combine, concatenate all these curves and create a one single curve that can be treated as the boundary of this entire region actually. Okay. So they may have whatever orientation, doesn't matter. Okay. Still. So can you give me a parameterization for C1? So C1 is a curve. Okay, so first of all, if mathematically it's a, so we're going to say, okay, this is important. If you want to know the parameterization of a curve, the question is, do you know its rectangular equation? If you know its rectangular equation, you know the curve actually. So what is the rectangular equation of this curve actually? Okay, so the rectangular equation means equation in xy coordinates. So what is the equation of this in xy coordinates? So y equal to phi 1 of x. So that's a rectangular coordinates. So if I have y equal to phi 1 of x, so what would be the parameterized form of it? And I know that x is between a to b. Okay.
Phi 1 of b.
So it's going to be what? Parameterization. I want to see them as the curves.
So t comma phi.
Yes. So the parameterization is going to be really the map t. Okay, the path that it is going to represent, let's call it a P1, is going to be a map from A to B, and that maps a point, into say R2, and the definition of it is going to be the P1 of T is equal to T and phi 1 of T and phi 1 of T. Okay? So I don't need to tell you that C3 is also going to be have parameterization P3 with the definition same. It's going to be T and phi 2 of T.
Yes.
What would be the parameterization of C2? You may assume it's a line actually. Okay. So what would be the parameterization of it? T, bus. Yes, T, okay. So you are so much, Very. या एक और तरीका भी हो सकता है. There is another thing. So what are the coordinates of this point? एक और चीज भी. If I can find a rectangular equation for this in the terms of x, y, I can find a parametric curve. The question is, how can I find the equation of it? So what is this point? So the input is A, while the output, this lies on this curve actually, so we're going to call it, this is phi 1 of A actually. Right?
Yes.
How about this point? So it's going to be B and phi 1 of B. So I have a line whose 2 points are known to me.
Phi 2 of B होगा.
Phi 2 of B होगा, sorry, yes. नहीं B क्यों A होगा ना? Still the point A है. Phi 2 of A. ठीक है? So I have a line whose 2 points are known to me. So can I find its equation? So I can find the equation y equal to so and so, and then I'm just writing the parametric form of it is going to be phi, for example, 4 is going to have, okay, so it's going to be t, okay, so t, just writing it directly, okay, or maybe a, and 1 minus, because x is fixed, x is not changing, if the y is changing only. Okay, so 1 minus t phi 1 of a plus t, okay, phi 2 of a. This will be the parameterization of it actually. So let's find the equation of the line. This will be the value of the line, the way it varies. How about C3? So this point is like b phi 1 of b. This point is like b phi 2 of b. So the C3 is going to be, t and 1 minus t phi 1 of b plus t times of phi 2 of b. Okay? So this would be the parameterization of it. Okay? I want to see this entire guy as a single curve. Okay? So what should I do?
Concatenate.
I need to revert the orientations first.
Yes.
Okay? So C1, this would be C2. So this is going to be now C3 bar actually.
Yes.
Okay? And this is going to be C4.
C4 bar.
Okay? And I can give this entire curve a name, and the curve can be seen as a C1 concatenated with C2 concatenated with C3 bar concatenated with C4 bar. Okay? C4. Are we happy with it?
Yes.
We are already doing the proof of green theorem actually. Okay, so I'm going to just write all this as obviously an integral, but I'll tell you that how the line integral can allow you to compute, how the line integral in these areas are related with each other actually. Okay. So now let's assume that on this region S, I have a P defined actually. Okay, that takes values in R, and it's a continuous function. Okay, so it's a scalar field. Okay, scalar field. Huh? And I want to integrate this scalar field over the curve C, the entire curve C. Okay. So if you want to compute the integral of this over the entire curve C, and all these are concatenated, then this would be what? The integral of this C1 plus the integral of P over C2 minus integral of P over C3 and minus integral of P over C4. This would be like that actually. Okay, because you have reversed it curve actually, so you can have a negative sign there. So let's compute this guy now. C1. Okay. C1. So how can I compute it? So the integral of this is going to be integral of C1 plus C2 plus C3 bar plus C4 bar. But I know that integral of a curve and its, what do you call, integral over a reverse curve are related with each other by only minus sign. They differ by minus sign.
ये सब डायरेक्शन की वजह से आ रहा है।
डायरेक्शन की वजह से आ रहा है, ठीक है। बट ये थ्योरम भी है, so I want to compute it. So what should I do? So I need to take my parameterization P1 of t and substitute it into the curve. Obviously integrating from A to B. Okay. And what should be the next thing multiplied with it? The magnitude of the magnitude of P prime of t actually. So what would be the magnitude of it actually? क्या होगा?
So यहाँ पे P किस चीज को शो कर रहा है?
So P is a scalar field मेरे बेटे.
सर ये हमने इन्हें ऐड कैसे किया सर, किस प्रॉपर्टी को यूज करते हुए ऐड किया?
बेटा ये हमने ओके सो इसका मतलब एक्सरसाइज सॉल्व नहीं किया अभी तक, ठीक है? So we have a result that if you have a scalar field and you want to integrate a scalar field on a concatenated curve, then what you can do, you can compute their individual integrals on the curves and sum them. Okay? That's what essentially it means. And so what should I do? What should I do? So this is a scalar field that I have to integrate on the curve C, C1. So how can I compute the integral of a
Derivative now.
So you have to take the derivative and norm. So what would be the derivative of this parameterization?
Derivative. P
The other thing could be, okay, another way to do it is going to be the shortcut one actually. Okay, maybe if you don't get too much in the details. So the other thing could be that I want to integrate this p of xy, okay, over this dx along the curve C, because when I am moving along curve C, the only thing that is changing is this axis. Okay, and so how can I have it? What is x on the curve on C1? What is x on the curve C1 actually?
So
X of t is t. Isn't that t?
Yes.
So x of t is t on the curve C1 actually.
Yes, sir.
Okay.
And y 5
So you're gonna say, can I say this would be same as that integrate over a to b, this p of t, phi of t, okay, multiplied by, okay, dx by dt times dt. Would you agree with me? Why this would be the case?
So x of t is equal to t.
X of t equal to t. Okay. Now,
It will be 5 1 sir.
J,
It will be
5
5 1.
1 obviously. It's going to be obviously 5 1 of t. Okay. So if I simplify it a bit more further, so it's going to be p of t of phi 1 of t and dt. You can simply write it in this manner. Okay. Reflect upon it. If you have question to us, let's think over C2.
ये dt वाली बात समझ नहीं आई
कौन सी?
सर ये हम dt दे भी रहे हैं
कहाँ दे रहे
और
हैं?
ये पहले डिवाइड किया था फिर यहाँ पे मल्टीप्लाई कर रहे हैं
But x of t is t actually. So even if you put dx by dt, that will become 1 actually. So it's not going to make it. So we're just transitioning from rectangular coordinates to its parametric equation. That's what we're doing. So you want to integrate b over the C2. Anjay? So you have to do what? C2, okay. चलो ठीक है, जो भी है हम अपने तरीके से करते हैं, जरूरत तो नहीं है कि हम इसको फॉलो करें. So whatever notation we have done, let's do it in this manner actually. So the C2 is this x, this line actually. So what do you think? What would be the outcome in this case? I mean, this is again going to be same as a to b, p of t, okay, and maybe okay p of.
सर C2 का कर रहे हैं सर.
चलो ये करो ना p3 of इसकी जो पैरामीटराइजेशन है p2 of t, right? So let's give it a name p2 of t. ठीक है, इसकी जो पैरामीटराइजेशन है, I'm giving it a name p2 of t. Okay? Multiplied by dx by dt and dt. What is x on this curve?
Constant.
So it's a fixed number. So everything would be there. This is there. Okay.
Yes, sir.
This integral is zero. And for the same reasons, integral of p over c4 is also zero. Okay? Can you guess what would be the value of the p onto the curve, say c3? So if this is p of t, phi 1 of t dt from a to b, so
सर
this would be
y2 हो जाएगा सर.
yes, p of t. Convince yourself about all this stuff beta. ठीक है?
सर इसमें जो लिमिट होगी वैसे तो ये हमारे पास इंटीग्रल 0 होगा, लेकिन लिमिट क्या सर a to b होगी सर.
Limit a to b होगी तो होगी.
सर C2 तो
Okay, so नहीं a to b नहीं होगी, but let's keep it c2 actually.
ओके सर.
But whatever that would be,
सही है सर.
so shall I write a to b? This is a good part. Now the t goes between 0 to 1, so you can You can have it.
0 to 1
सर 0 to 1 नहीं दिया है हमने
नहीं ठीक है
फंक्शन आएगा
ठीक है so let's keep it as it is actually.
Yes.
Okay? So let's keep it as C2 itself and then you know why this is 0 actually. So what would be the final conclusion of this? So compute the integral of P over the curve C and it turns out to be the integral from A to B of P of T phi 1 of T minus P T phi 2 of T and dt. This would be the concept.
हाँ सही है
And it's a definite integration. So no matter what variable I must use, it should be. So it's not going to make any difference actually. Okay. A to B, for example, if I put say x phi of x, okay, phi 1 of x, phi 2 of x minus P of x phi 1 of x dx is going to be the same actually. ठीक है?
सही है माइनस कॉमन
Now, I mean, if you think, you can argue from many different perspectives. If you see this as a function of, for example, y, okay, you can apply mean value theorem. I can do what? So that would be the derivative with respect to the y multiplied by, mean value theorem क्या होता है roughly? Or you can apply a second fundamental theorem of calculus. Everything would be fine actually. So here's the thing. Can I say this is same as that I am integrating the partial p by partial y with respect to dy? Okay? From the curve phi 1 of x to the curve phi 2 of x. Would that give me the same result?
यस
You're integrating p with respect to why I'm writing partial because x is the same in the both cases actually. And integrating with respect to y give me the same result. And I have dx actually. Okay? And this by Fubini theorem would be equal to the minus, okay, integral over the entire s, okay, and partial p by partial y and dx. ठीक है? So I can already see that this formula allows me to convert a line integral of a scalar field p into a double integral, or other way around. Okay? Or other way around. If the integrands, so if this integrand is really this integrand is really the derivative of this integrand actually. Okay. Now, I'm not repeating all calculations, but I'm just concluding and directly writing. What if you have a Fubini type 2 region actually? So if S is type 2, if S is type 2 and Q is a map from S onto R, then what would be the line integral of the curve C that can be treated as the boundary of the Fubini type region type 2, okay, would be what? And integrating Q over it. So this would be equal to the double integral. Okay, you can repeat all this analysis and now you will see there will be no minus here actually. The partial Q by, so here you have partial Q by partial y, so now you're going to get partial Q by partial x and say dy dx or dx dy dx. ठीक है जी. So these are two important results. Now I am in position to define what do I mean by a green region. Okay. Green region and the green theorem. So the green region is, I'm going to say S, that is subset of R2 is green region if it is type 1, S is type 1 and type 2 both. So first thing. The green region is what? It is type 1 and type 2 both. So a rectangle, so a circle, so an ellipse, so these kind of closed figures are in the green regions actually. And boundary of S